real numbers. Let us recall natural numbers which are denoted by n. They are 1, 2, 3, 4, 5. We write them in the form of set. When we include number 0 in this set, we get another set, which is the set of whole numbers represented by letter W. Hence, W includes 0, 1, 2, 3, 4, 5, and so on. For every natural number n, we have a new number which is opposite of n and is denoted by opposite of n, such that when we add these two, the result is 0. Hence, n plus opposite of n is equal to 0. Hence, for every positive number like +1, +2, and so on, we have their opposite number -1, -2, -3, and the list moves on. This set of numbers, which includes natural numbers, 0, and opposite of all natural numbers, is called a set of integers represented by I. Now students, we have come across and worked with numbers like half, 1/4, 2/3, 3½ and so on. These numbers are called fractions. This set of numbers, which includes fractions, integers, is called the set of rational numbers and is represented by letter Q. Now we define a rational number as P upon Q, where P and Q are integers and Q is not equal to 0. Therefore, all integers according to the definition is a rational number, because for integer P we can write P is equal to P upon 1. So students, set of natural numbers n is subset of whole numbers W, which is subset of integers I, which is again a subset of rational numbers Q. Now students, we can represent these numbers on the number line. All the positive numbers are represented to the right of 0 and the negative numbers are represented to the left. We already know the order relation of the numbers marked on the line. As we move towards the right, the value of the number increases, and as we move towards the left, the value decreases. Hence, -3 is less than -2, which is less than -1, which is less than 0. +1 will be greater than 0, +2 is greater than +1, and so on. Now let us understand equality relation and order relation between two rational numbers. If first rational number is represented by P upon Q and second rational number by R upon S. Equality relations. If Q and S are greater than 0 and P upon Q is equal to R upon S, then P multiplied by S is also equal to Q multiplied by R, that is, PS is equal to QR. Order relation. If P upon Q is greater than R upon S, then P multiplied by S is also greater than Q multiplied by R. Properties of addition of rational numbers. Students, you are aware of how to add and multiply rational numbers. Let us quickly revise and name each property which you are already aware of. 1. If A, B, C are rational numbers, then A added to B is same as B added to A. This property is called commutative property. 2. The result obtained when C is added to the sum of A and B is same as when A is added to the sum of B and C. This property is called associative property. 3. When 0 is added to A, the result is A. This property is called additive identity. 4. For each rational number A, there is a rational number minus A with property that A plus minus A is 0. This property is called additive inverse. Properties of multiplication. 1. The product obtained when A is multiplied by B is the same as when B is multiplied by A. This is again commutative property in the operation of multiplication. 2. The result obtained when C is multiplied with the product of A and B is the same as when A is multiplied with the product of B and C. This is associative property. 3. When A is multiplied by 1, the result is A. This property is called multiplicative identity. 4. For a rational number A, where A is not equal to 0, there is a rational number 1 upon A such that when you multiply A and 1 upon A, the result is 1. This property is called the property of multiplicative inverse. 5. When A is multiplied by the sum of B and C, the result obtained is the same as the sum of A multiplied by B and A multiplied by C. This property is called distributive property. 6. If the product of two rational numbers A and B is 0, then either A is 0 or B is equal to 0. Exercise 2.1. Question 1. Represent the following rational numbers on the number line. 1. Now students, let us plot some rational numbers on the number line. We begin with -4, 3, -2, 0, 4. There can be no difficulty in plotting the above numbers. Draw the number line and mark -4, 3, -2, 0, 4 at the appropriate place on the line. 2. Now let us plot 11 upon 2 and -5 upon 2 also. To plot fractions, convert it into improper fractions or decimals. Step 1. Convert it into decimals. Step 2. Now since 11 upon 2 is equal to 5.5, it will lie between 5 and 6. Step 3. Hence, divide the space between 5 and 6 into 10 parts using a ruler and then mark the fifth part as 5.5. Step 4. Similarly, following step 1 and 2, let us plot -5 upon 2, which is equal to -2.5. Step 5. Now since -5 upon 2 is equal to -2.5, it will lie between -2 and -3. Hence, divide the space between -2 and -3 into 10 parts using a ruler, and then mark the fifth part as -2.5. Question 2. Write the rational numbers in decimal form. 1. Let us consider the number 3 upon 5. Now, 3 upon 5 on dividing is equal to 0.6. Here, the integer part is 0 and the decimal part is 0.6. Such a rational number is called terminating part. Let us now consider 1 upon 6. On dividing, we get 0 as the integer and the decimal part begins with 1. And on further division, we repeatedly get 6. Here we can realize that we cannot end the division. Since 6 is repeated after 1, we write 1 upon 6 as 0 followed by a point and then 1 and 6. Then we put a bar on 6 to show that it is repeated or recurring. Such a fraction is called non-terminating or recurring. Whenever there are more than one number recurring after the decimal as in 0.4545, then we show it by putting a horizontal line on the recurring numbers. Therefore, 0.4545 is equal to 0.45. A rational number p upon q is a terminating decimal only when prime factors of q are 2 and 5 only as 1 upon 2, 3 upon 5, 7 upon 16, etc. Problem set 2a. Question 1. 1. Students, let us go ahead by now expressing a recurring decimal in the form of p upon q. We take the following recurring numbers. 1. 0.4747 recurring. 2. 9.315315 recurring. Now, 0.4747 recurring can be written as 0.47 and a bar sign on 47, which means 47 is recurring. Now, let us consider x will be equal to 0.4747, that is 0.47. Since we have two numbers recurring, we multiply both the sides by 100. X into 100 is equal to 0.4747 recurring into 100. Hence, 100x is equal to 47.4747 recurring is equal to bar 47.47. Now, subtracting statement 1 from 2. Therefore, 100x minus x is equal to 47.47 minus 0.47. By solving, we get 99x is equal to 47. Hence, x is equal to 47 upon 99. Hence, 0.4747 recurring in the form of p upon q is 47 upon 99. That is, p upon q is equal to 47 upon 99. Question 1 to 9.315 recurring. Let x be equal to 9.315 recurring is equal to 9.315. Multiply the entire equation by 1000 since the recurring sign is on 3 digits. Therefore, we get 1000x is equal to 9315.315. Now, subtracting statement 1 from 2. 1000x minus x is equal to 9315.315 minus 9.315. Now on subtracting, we get 999x is equal to 9306. Therefore, x is equal to 9306 upon 999. Therefore, x is equal to 1034 into 9 upon 111 into 9. Therefore, x is equal to 1034 upon 111. Question 2. Write the following real numbers in decimal form. 1. Square root 2. Determine the value of square root of 2, which is written as number 2 under the square root sign. On solving by the division method, we get that square root of 2 is neither a terminating nor a recurring decimal. The result is a non-terminating decimal. Such numbers which do not end in as a terminating decimal or a recurring decimal are called irrational numbers. Similarly, square root of 3, 5 and 10 are other examples of irrational numbers. The set of irrational and rational numbers is called the set of real numbers denoted by R. Therefore, the set of rational numbers denoted by Q, which is a subset of real numbers denoted by R.